Hey everyone, today I'm going to be showing you the local linear approximation for logarithms in this case. So this is sort of a follow-up to my old logarithm video that was absolutely horrendous and completely wrong. But this time we're downgrading it a little and using logs of the same base because I don't know how to do it the other way. So we want to estimate log base 10 of 11 given that log base 10 of 10 is 1. So I have the steps right now. It's just step 1, find the derivative. So we can generalize the function here to be, so we'll say f of x is equal to log base 10 of x. Therefore, we want our derivative, which would be f prime of x. So prime of x is equal to, and the derivative of log base 10 of x is 1 over x ln 10. So that's step 1 completed. And so step 2 is find dx. So since I just stated that the little number, not our base, but what we're trying to find the log of is x, we want to find dx, or the change in x. So in this case that would be 11 minus 10 is equal to 1, positive 1, that's important. You should do it in that order specifically. The one you're looking for subtracted by the one you know. And now we plug in the known value of x into our derivative. So we know what log base 10 of 10 is. So we can plug that in to 1 over x ln 10. That would get you, I'll write it out, that would get you 1 over 10 ln 10. And even though the point of this is to do this without a calculator, I don't know how you would estimate this. But I've already written it out, so we're going to pretend like we need to do it without a calculator. So it's 0.043249. Now that we know that that's an estimation, decimal approximation of 1 over 10 ln 10, we can now multiply the result of this step by dx. But since dx is just 1, we don't really have to do anything. It's just still 0.043249, and now we need to add this value into our known log value. So step 5 says add dx. It's not exactly dx, it's add the result of multiplying dx by step 4. So in this case that would be 1 plus 0.0432, that is an awful 249. And that gets you 1.0434, I just wrote that wrong, 3249. Oops. 3249. So we get that after that, that's the last step. So after we do this, we can kind of say log base 10 of 11 is approximately equal to 1.043249. Now, this is linear approximation, so obviously it's not entirely correct. So we can actually do it out on a calculator and find out what the real answer is. So we do, and it is 1.041392, approximately. We were pretty close with this approximation, being only about, like, what? 0.00, like 9 or something, is like 0.001 off. We were really close with this linear approximation, but I guess that brings to the real topic, linear approximation and how applicable it is to logs. Generally speaking, when you have linear approximation, you want two categories. You want your derivative to be small. So, for instance, when you estimate square roots, the derivative of the function square root of x is 1 over 2 square root of x. And that pretty much always gets you a decimal. There might be some fringe cases, I can't think of any of those, but for the most part, it gets you a decimal, making it so that your derivative is really small. Not only that, that's one part. The other part is that dx has to be small. If the gap between your x values, the distance or the change in them, is gigantic. For instance, had we been estimating log base 10 of 45, well, the closest one we have log base 10 of 10, and we have log base 10 of 100. So we can't really estimate that all that well because dx is just gigantic. We can't approximate that because it's local linear approximation. It has to be within the realm of whatever known value you have. Otherwise, you're going to get an outrageous number. So this doesn't work for everything. For instance, like if we tried log base 5 of 10 using log base 10 of 10, that's not going to get you a very good answer. And so it definitely has its limits. You can't estimate everything with local linear approximation, but that's how you would estimate at least this log, and you could probably do like log base 10 of 9, or like maybe log base 10 of 12 with this. And you could definitely apply those steps or that criteria for local linear approximation into any other thing you want to estimate, like cube roots, square roots, some other radical function that you can't just get off the top of your head. So yeah, thank you for watching.